Hi, so here's something we probably all know. If I take two different wires, in this case one of copper, one of nichrome, twist them both together and apply a heat at that twist, now what happens is it generates electricity. That's actually really fascinating because it's just two twists of wire. There's none of all that tedious mucking about with coils and lumpy magnets and brushes and making things spin. There's something magical about that. Now that was first noticed in 1794 by Volta. He did nothing with it. It was actually in 1829 when it's a chap called Seebeck did all the work on this. He noticed it independently and did all the legwork, and it's one of those rare occasions when somebody who does the work gets the recognition. So he went through recognising about 28 or so material junctions measured relative to platinum, because of course it's very difficult to measure one thing, easy to measure one thing relative to another, and he created a table. And this shows the metals that he looked at because he was working with metals. Unfortunately, of course, the kind of voltages you were looking at were in microvolts per degree of temperature, so really piddling. That meant for a very long time they were used for very little more than at temperature measurement, because that increase of microvolts per degree is constant. Because it's constant, because it was Seebeck who actually did all this stuff, it's called the Seebeck coefficient, and that effect is now called the Seebeck effect. And it was intensively looked at because I think just the magic of it. Unfortunately, as I say, those metal junctions weren't very productive. It was about 1929 actually when a chap called Ebenloff, he was a Russian, looked at semiconductors, and he produced this table of semiconductors. And if you have a look at that and compare it with the earlier table, you'll see we're now in millivolts per degree centigrade, which is a huge difference, and suddenly starts to make these things look like they might be able to do something. Because that fascination with them, right from when Seebeck was working with these, has led to an intense development of them, and a lot of work actually went into these junctions. Now if you have one, it's called a thermocouple. Bolt a whole load together to get some usable voltage and some usable ampage out of it, and it's called a thermopile. And it's called a thermopile in reference to the voltaic pile, which is a chemical battery with a stack or a pile of elements, and this is a stack of elements in a pile. So if you connect them all together, you get a thermopile, and what they were looking for was a thermopile that could produce some real energy. So of course Seebeck didn't have a whole bunch of raggles available to him, and his instrumentation wasn't that great, so he noticed the effect by actually deflection in a compass needle, and he thought the heat produced a magnetic field. It was Ørsted who took it up, and Ørsted actually got measurable currents out of it and suggested that the electric field is what was being generated by the heat, and the electric field created the magnetic field, and that's certainly the way we understand it at the moment. Somehow an electrical field is being generated, an electrical flow is being generated which creates that field, and that's hardly likely seeing as there's a relationship between resistance and heat. And of course the more resistant material is, and the moving the electrons by heat means you'll get the flow, so it's kind of understood that way at the moment. So it was Ohm, really, of Ohm's law fame, who did an awful lot of work with this, because prior to Ohm it was really just used for measurement. It was Ohm who sort of thought of as being the one who is credited with looking at the thermopile as a possible power generator. Of course, Ohm had his own problems, and there was a great joke around saying that Ohm's law is meeting great resistance, because nobody actually believed in him for ages. So as the decades rolled on, people of course were looking at this, but they were all metal to metal junctions. They started looking at things like the hot side, how to get it hotter, the cold side, how to get it colder, what kind of materials would work really well, and they ran through a whole load of gradual improvements of this device, but still basically metal to metal. The introduction of semiconductors instead of metal to metal will perhaps be a quantum leap between the mid to late 19th century to the early 20th century, and that great one in 1929, courtesy of our mad Russian scientist, which was this, the so-called Russian lamp. Now the first efforts of the Russians to create a thermoelectric generator was called the TG1. Running a radio from a thermoelectric generator wasn't unknown. There have been various attempts in the late 20s, early 30s to run gas-powered radios, and these were run from They were zinc nichrome junctions, and still needed a whole mass of material. And the early TG1s were also like that. So they were quite big, quite bulky, quite heavy, needed quite a lot of fire. But of course, the Second World War started. And during the Second World War, there were two desperate needs. The Partisan boiler. Absolutely fascinating. What it really was an inside jacket of water. And an outside jacket you put in the flame, and the thermoelectric junctions all the way in between them. And of course, the outside jacket could get to 700 or 800 degrees. But the inside jacket was going to stay around about 100 until all the water boiled away, and you basically just added more water. And that really was the landmark development of thermoelectric generators that could produce usable power in a very stable kind of way. And of course that led to the 1959 development. Really lofts zinc antimony Constantine semiconductor junctions that made all of the difference, and they were about somewhere between 2 and 4% efficient and generating sufficient volts. I think it was in the order of 50 volts were being generated in his lamp. They were used predominantly in the remote areas of Siberia and China and cost something like $56 to buy one. And they ran off kerosene lamps. Around about the same time, the Aztec 12 came out by the Minnesota Mining Company, and you have to ask yourself, did the Minnesota Mining Company actually invent this, or just nick it from the Russians straight away? Because they came out with their thermoelectric generator and a radio that it was supposed to run, and you could buy the two bits as a kit. But then we're entering the nuclear age, so the Americans went and bought a load of these and busily bolted them onto some nuclear reactors. And it was then that the thermoelectric generator was born. Of course, these days we have these available to us. They're often called Peltier devices, but actually Peltier is the opposite effect. They're Seebeck devices. But actually that's not true. They can be used either way, to be honest, but we do have these. They're available for about £5 to £10 for a size that size, and they generate considerable power. The power generation, remember, is the difference in heat between the hot and the cold side. So it's heat difference you have to be able to maintain, and these have been used in lots and lots of ways. I mean, the first efforts to use these as a nuclear reactor, a nuclear heat generator, is strontium-90, and of course now they use plutonium, and you find them in things like the Cassini probe. But you also find them in an awful lot of products. The most famous one, perhaps, is the BioLite thermoelectric camping stove. It's got a couple of Peltiers, sorry, my bad. Got a couple of thermoelectric generators slapped onto the side of the camping stove, and you can recharge your phone or run a light. And of course, Honeywell created one that was responsible for powering the boiler control. Also a product available called the LUFO lamp, which I believe has an AM radio built into the bottom of a heat lamp, which is kind of useful, I suppose, if you happen to be camping and want some light and radio at the same time. So these things aren't dying a death. They're like lots of things. They began as pretty poor, really, in terms of their output, but were absolutely fascinating in terms of their application. Developed over a few decades to be something that is immensely useful, and of course we're looking now at producing devices that are even more efficient than the ones that we've had, and for that we're starting to look at graphene. And the Partisan battery fulfilled a need. There was a war on, there was a lack of electrification and a need for communication and recharging batteries, so the Russians developed the Partisan battery, which was absolutely awesome. It really used a couple of pans and a 1930s version of this. We have these Peltier devices, our Seebeck devices, that we can use, and that's what we're going to use instead of linking up a whole load of zinc and Constantine. Now the great idea about the Partisan battery was heat control, because these things generate by heat difference, because you stick them in a fire, the other side gets hot really quite quickly, and cooling one side can be challenging. You see huge arrangements of fins to do that. Well, the Russians thought about doing was, if we stick some water in a fire, then when the fire hits the water, of course it's 600-700 degrees centigrade, but the water side can never actually get above 100 degrees because it's boiling. So they stuck some of these between two pans and filled the pan with water, stuck it in a fire, boiled the water, and of course they got that heat control, and it's such a stunningly simple solution to that problem. I thought I'd give it a go making one. In order to make one, what I've got is two aluminium pans, and one pan fits neatly inside another pan. So what I'm going to do is take a whole bunch of these, stick them in there, pop that on top and we'll see if it works. Now to do that, I've got to make this fit into here. So I'm going to remove this handle, which is easy enough. There's a screw right there. Okay, so there's the handle removed, and I've taken 4mm off of that by sawing it off, because I want that to be a little bit proud. I want it to be proud because I want to put some insulation in there, and of course I have to make a space to fit the modules. So obviously as many of these modules I can get on there is going to be important. I've also sanded the bottom of this so it's flat because it had a slight dimple in it, and remembering which one's the hot side, I can get 3 on there like that. Now because we're putting these in an enclosed space between 2 layers of metal, we're going to get 3 issues. The first one is you can't solder them. So if you solder them, the solder will probably melt. So what you do is you put a bare crimp on it. The other one is, this is highly likely to char. Now you can't have that obviously because it's on a layer of metal, so it'll short circuit. So what you do is use this stuff. This is high temperature sleeving. You can buy it online or you can recover it from toasters, and it's fine up to about 1200 degrees centigrade or so, and the wire coating will char, but this won't. You don't worry about the wire coating. What you're worried about is it touching the metal, and so that acts as a high temperature insulation. So you just put some sleeving on it, and then we put the other side in there and we can seal that up nicely, and that means that we're protected from the heat destroying the joint and the heat destroying the cabling. And the other thing of course is heat transfer. Now we don't really have to worry that much about the hot. The hot's going to get hot. It'd be better if it had a transfer medium because it would be more efficient, but it's not such a worry as the cold side. We need to make sure that we have good contact between this and this. Now there's a number of ways to do that. As you know, Luke's been experimenting with our ink and apparently that's brilliant. The other if you want is a thermal paste used for computers, but perhaps one of the best things is this stuff. It's graphite foil. This is used a lot for heat transfer. I happen to have some, so that's what I'm using. If you don't have any thermal paste, pop your graphite foil on, pop that on, and then when we close that, it'll compress the foil against the pan and against this and make a good contact. Okay, you'll notice I've drilled 3 holes in this pan at 120 degrees apart, and we're now ready to assemble. So, grapho. Don't forget which side is the hot side, and then in with your thermocouples. Then the other piece of grapho. Then we can shove that pan in, and we want to shove it down tight. Once you've shoved it down tight, put some weights on it, we can drill through those holes and bolt the whole thing together. And there it is done. The only thing left to do with it now obviously is put some water in there, bring it to boil and see if we get some readings. Okay, we can see that voltage rising. And it's going to. It's a bunch of Peltier devices. But there is a slight disappointment really about these modern devices. This one, which is about £3.50, is labelled as high temperature. And that means in those terms it'll only go up to about 200 degrees centigrade or so, which means that we will be able to boil this water eventually. But if I were to put this directly in a fire on a hob, I can expect 500 to 600 degrees centigrade. And if I want to buy one of these with that, with the ability to withstand that kind of temperature, you're talking about £300 to £400 for a unit that size. So really not very doable. We have to accept the limitations on this, which means that we're not be able to apply a lot of heat to there, or we can guarantee in destroying them. And I've got 3 in here, remember. So what that also means is to get some usable power out of it, I need 10 or so really. I mean, this will light an LED when the temperature gets difference gets enough. We can draw some power, charge some phones, that sort of thing from 3 of them. But it will take a little while to get there, and we can't put that up to a ridiculous temperature. Everything's going to explode. That's actually reasonably quite cool. It's lit the LED strip and quite brightly, and it's a 2.67 volts, so the turn-on voltage of that's around about 2.5, something like that. But it works, which is kind of astonishing really, and as I say, it's going to be a while before that boils, but we managed to keep the cold side cold and the hot side hot. Okay, so we got our modern interpretation of the Partisan battery working, and I thought it was kind of cool really. It'll be a while before we boil that water on for candles obviously, and I think it's an example actually of where these modern materials are in fact not up to the job in the same way that the old materials were. The original Partisan battery is supposed to be able to boil you a kettle full of water and charge a 12-volt battery to run a radio set. And this is a 1940s radio set, so they were pretty power hungry. Think if I'm going to improve that, I'm going to have to take it to pieces and replace it with the original thermocouple, which was a, memory serves, a nickel antimony semiconductor and a constant tin metal on the other side and something like 300 junctions. And that is what the Partisan battery is supposed to be. But we got our modern miracle working, and it worked and lit a light and put out some power and maybe enough to charge a mobile phone, so it was pretty cool. And I was disappointed with it on a number of levels. One of them is that in there are some of these, which are a modern day Peltier stroke Seebeck device, and they're disappointing. They're disappointing because of the limitations on them. You can't go over 200 degrees centigrade or you pop it. And I know that because I popped a few trying it. So they just won't work above that kind of temperature. And of course, what I really want to do is strap this onto a rocket stove, of course, because we're still working with the rocket stove, and maybe make a better Partisan battery. And for that, we're putting fire there. So it's going to be sort of 600, 700, 800 degrees centigrade, and these are not going to last. Now, these are made out of semiconductors. If I take these apart, what I'll find is blocks of semiconductors. Let's say that's a bit of P conductor and that's a bit of N conductor, and they're set up like this. So there's a separation between them, metal plate across the top, and then a couple of metal contacts. Then some ceramic top and bottom. You heat here, and the heat flow goes that way. And because the heat flow is going that way, we get a current driven along here, and that's why it generates. Now that's one architecture, one way of making them, and that's the way that this is made. There is another way. You can remove that, bang them together, put the contacts there, heat goes there. This is cheaper and simpler because of course there's no top plate. Same thing, heat flow from the top to the bottom drives a current from here, but now it drives it across the PN junction and then back out again. And these are obviously called PNTEG architecture. But they remain semiconductors. Because they're semiconductors, they have that temperature limit on them. Now they do generate an awful lot of amps, well microamps, but they do generate a lot for what they are, but they have a severe limitation for the application that we want to use them for. In video 1416 we looked at an alternative material that I actually really quite like. I like it because it can survive much higher temperatures. It has its own drawbacks, obviously. It doesn't generate as much, but at a single junction it will generate 300 millivolts or so, and we made a 16 junction device and lit up some LEDs with it. So it does a reasonable job, and of course we can cope with that very high temperature difference being what's important. But I made it like this. It's a bit of wire there, and if I heat that bit of wire until it's glowing, I'm putting it in this bit of the flame, which is the oxidizing bit of the flame. There we go, it gets covered in copper oxide. That's now ready to use. All I have to do is take another bare copper wire, pop it on the copper oxide, stick it in the flame, and we're going to generate. There we go, 253 volt, 0.253 volts, quarter of a volt from just that. That's a few microamps, but it's a quarter of a volt from just that one thing. Problem is getting it to stay there. We made that wheel and used the length of the wire to stabilize it, but if you want to stick it in a pan or a compact device, that's obviously not the best arrangement because you can't really tighten that down. If you tighten that down, you'll break this very thin copper oxide layer, which is what the heating does, and you'll make a contact and the thing doesn't work. So you can't tighten it too much, and you can't have it too slack, because if it's too slack, of course, it will fall away. And I have tried various things, various ways to try and bind it onto that to make a stable device, and it's proving very difficult with wire. And that's made me think, okay, if it's that difficult with wire, maybe it's just because it's thin. Let's try a plate. So I took a copper plate, did exactly the same thing, that is, heat it until it went blue-black, and that blue-black is copper oxide. That's black copper oxide, underneath is red copper oxide. And that prepares the plate. Then I took my wire, which was just like notice that. I put a little bend in it, and that's because I don't want this edge scraping it. Now, heat it, touch that loop on it, and we get exactly the same thing. We get about a quarter of a volt plus being generated out of that. And to prove that generation, what we can do is take a capacitor and connect that capacitor up so that it's feeding directly into the capacitor. And then we can measure the voltage across the capacitor, and what we get is a stored charge. It's generating voltage, it's storing that charge in the capacitor, and we can use that charge later. Okay, so I've got it connected to a capacitor, and if I set my thermo generator going again, touch it, loop on there, and we can see that it begins to charge the capacitor, and this time of course that is real charge being put onto the capacitor. Now obviously it's temperature different, so even though I'm not applying the heat, that plate's quite hot, and so it's still being driven across in the same way that we looked at the NP junction. And if I actually disconnect that, you'll see the charge is being retained, and that's because that capacitor is actually charged. There's real power in there, we can do something with it. Now, I only used one loop and at one point on that plate, and of course the very next question you have to ask, or you would want to ask, is will two loops do it? Because one loop does it, will two? Okay, so I've discharged the capacitor, and this time I've got two loops here. If we apply the heat and touch it again, now this time, as far as I could tell, it charged twice as quickly. So one works brilliantly, two works just as well, and it should continue going up, because when we take our loop bit of wire and touch a point, we're just having a point contact. Of course, we've got lots of points that we can put there, so we begin to get a very heat resistive thermopile that's quite simple to form, because we have our copper plate, and that plate is the bit that goes on the heat source, like the fire or the oven or the rocket stove, whatever it is. And then on top of it we have another plate with lots of little legs with rounded edges that just sit on it. And they sit on it because they've got lots of little legs, so it'll take a lot of weight while it sits on it. So it just sits on top there, and they make point contacts. As this plate gets hot, then we'll get more driven through there in terms of amps, but roughly at the same voltage, 300 volts or so. So how do we increase that? Well, that is in effect a parallel connection. So if we take that top plate and connect it to the next bottom plate, we'll get an in-series connection, and we can build up the voltage that way. Alternatively, of course, we could always just charge the capacitors straight. So we charge them by connecting a capacitor to each one of these, and we discharge the capacitors in series. So we can charge the capacitors in parallel and discharge them in series to get the voltage we require, or we can connect these up in series using lots of point contacts across a copper plate to develop the voltage, the ampage that we need, and connect them in series to develop the voltage. So I think that copper oxide copper thermocouple, which is very robust, is a possible way forward. And one of the things that I really like about it is, of course, we can make it. So it's something that can be made from materials lying around that generates, as I say, one point contact generates 0.3 of a volt, so it generates quite a lot. Anyway, I thought I would share that idea with you. I've been working on it most of the day, and I'll build an actual one probably in the next video or the video after, but I wanted to share that because I found that quite exciting, that the copper oxide thermopile that we constructed in 1416 makes a very good candidate for an improved Partisan stove. Improved in the sense that it's much more robust to high temperature and much more within the capability of everybody to just get up and make. Anyway, I hope you enjoyed the video. I hope you found it interesting. Thank you very much for watching, and please like and subscribe.